Hello everybody, this is Dr. Christopher White and welcome back for part 3 of Sedimentary Rocks part 1. So before we go any further, let's just get the code word out of the way. The code word for this presentation is thunder. I repeat, thunder, 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 like the weather. So please make sure you write that down, put it somewhere safe because you're going to need it for the code word quiz. Okay, so we were just looking at dunes in the previous slide, so now let's have a think about ripples. So if you've been to a beach or if you've actually looked in rivers, there's a very, very good chance you will have seen some ripples. So ripples look like this. I mean, not particularly complicated things. So a ripple has a high point, which is the ridge, and a low point, which is the trough. So it goes ridge, trough, etc. So ripples are caused by the movement of sediment by a current. Most ripples are associated with sandy sediment, so you'll often find them in environments where you get build-ups of sand, so deserts, beaches, rivers. Now the really good thing about ripples is ripples actually come in two different varieties. So the first type of ripple we have is something which is called a current ripple. So a current ripple is asymmetrical, so one side of the ripple is a different length and different angle to the other side. Now this tells us that the flow of sediment that created this ripple was unidirectional. It only went in one direction. So a good example of that, the kind of environment we'd be thinking of, would be something like a river. A river only flows one way, so the sediment only gets transported in one direction. That is a unidirectional flow. And so these unidirectional flows will create a current, and so the ripples produced by that current are called current ripples, and they will be asymmetrical. So if I just jump to this slide here, these are going to be examples of current ripples. So one side is long and low, and the other side is shorter but steeper. And so you can see the ripple itself is not symmetrical. One limb, long and low angle, the other limb, shorter and steeper. And we can see it here. So here's an example of ripples left in a sedimentary rock. We can see in this case, so here is our long low face. So we're coming up here, we hit the crest of the ripple, and then we come down. So this is going to be our short steep face. So we're coming up, down, up, down, up, down. And so obviously this long low angle side, this is the side that gets hit by the water. And so this side of our ripple is the long low angle side. This is getting hit by the water. So we know therefore the water must be flowing that way. And so as we know that this is the long low angle side, this is the short steep side, we know the flow must be going down to the bottom left. And so as a geologist, what you would do is obviously you would take the bearing of this flow, and that would tell you the paleocurrent. So which way was the sediment being transported, when this was being deposited as fresh sediment. So the other type of ripple that we have is called a waveformed ripple. Now the thing about a waveformed ripple is that it's produced by a bidirectional flow. And as the name suggests, waveform ripples are associated with waves. So you're going to get them in beach environments. So think of a wave. A wave hits the beach and it pushes sediment up the beach, and then eventually it will slow down, lose velocity, it will stop, and then gravity kicks in and it pulls the water back down into the ocean. So what happens is you've got sediment being pushed up the beach one way, and then that sediment gets pulled back down the beach as the wave retreats. And so what you have is a flow in two directions, a bidirectional flow. And this is going to produce a symmetrical ripple. So here's an example of a symmetrical ripple. You can see one limb and the other limb, and both limbs are the same angle and the same length. And so this is telling us the flow of sediment was from left to right, and then it went back from right to left. So the flow of sediment is in two directions at 90 degrees to each other. Sorry, 180 degrees to each other. I do apologize. So the sediment was being transported one way, and then it came back the other way. And so this constant bidirectional flow produces a symmetrical ripple. And so this is why ripples are so cool, because if you can find ripples in your sedimentary rock, the first thing you'll work out is, are they symmetrical or asymmetrical? Well, if they're symmetrical, you know you've got to be in some kind of environment where you have where you have waves. So maybe you're on a beach, or maybe you're in an environment something like a tidal estuary, or maybe you're on the edge of a lake, for instance. Those are the types of environments where we might get waves. In contrast, if we start seeing asymmetrical ripples, well, then we know we're in some kind of environment where the transport of sediment is just going in one direction. So we're instantly going to start thinking environments maybe like deserts or rivers. And so ripples are extremely helpful in trying to work out what's going on. So the final type of physical structure we're going to look at is mud cracks. And mud cracks are associated with clay-rich sediments that are wet and are allowed to dry. And as the sediment dries, it will contract and it will crack. And this produces rather distinct fractures, which we refer to as mud cracks. And so the presence of mud cracks in your sedimentary rock tells you have an environment which undergoes cycles of wetting and drying. So you have a wet sediment deposited, and then that wet sediment is allowed to dry, and then new sediment gets deposited quickly over the top, filling the cracks in the muddy sediment. So we tend to get mud cracks associated with environments like lake margins, river banks, river floodplains. You can also get them along the seashore where you have muddy sediment, so areas like estuaries and deltas. Essentially, all you need to have is a wet, muddy sediment that you expose and allow to dry out, and they will naturally crack. And then the final thing you need those cracks to be rapidly covered over by new sediment. Because if they get covered over by sediment slowly, then the clay will just rehydrate and the cracks will be lost. If, however, you manage to get sediment deposited over the top quickly, that will fill the cracks before they have a chance to rehydrate and heal themselves. So here we have two examples of modern mud cracks. So we have a very mud-rich sediment that's been allowed to dry out, and you'll see you end up with these rather distinctive polygonal shapes. So most of these will have a minimum of 4 sides. Most will typically have 5 sides to them. And so these are modern examples, and these are examples from the rock record. You can see these are the cracks running through here. So you can see them there. So this piece here, for instance, would be the same as this piece right here. Okay, and the material we can see around it would be sediment that's filled the crack there. Okay, but remember, we need to fill these cracks quickly, because if we don't fill them fast enough, this clay-rich sediment will rehydrate, and then the cracks will be lost. And so the presence of mud cracks not only tells us we have a wet sediment that's been allowed to dry out, it also just shows us that the sediment was then rapidly covered over by new sediment later on. So we need to make sure we're thinking of an environment where that can happen. In the case of this picture here, what you can actually see is you can see the imprint of the mud cracks. So this sandstone here was actually the sediment deposited over the top of the mudstone. And so what you're seeing is the sand that filled the cracks. The mudstone itself has been lost, but because the sandstone is more resistant to erosion, it's been, it's preserved, and so we can actually see the imprints of the mud cracks on the bottom of our layer of sandstone. But nevertheless, once we can see mud cracks, we have some idea of the type of environment that we could be in. Okay, so those were physical structures. Now let's think about biogenic sedimentary structures. So sedimentary structures are related to the action of life. And so straight away, if we look at this sediment here, we can quite clearly see we have some burrows, don't we? You can see them there. And so this is a biogenic sedimentary structure. So biogenic structures are helpful because they are the deformation left behind by the action of organisms on sediments. So examples of biogenic structures are things like tracks, trails, burrows. Such features are also referred to as trace fossils because they are an indicator of the organism having been there, but they aren't actually the fossil of the organism itself. So extensive burrowing can actually be bad though, because extensive burrowing will disrupt the sediment, and so we can actually lose physical sedimentary structures. This is a process called bioturbation. So if your sediment gets, churned up through the action of lots and lots of worms, for instance, burrowing through it, your sediment is described as having been bioturbated. And that means you'll lose the physical sedimentary structures, which can be quite annoying. So here we can see some examples of some trace fossils, or to put it another way, biogenic sedimentary structures. So here we can see a burrow. And so you can see, so this is actually the opening of the burrow. So this would have been the seafloor here. And you can see the particular organism produced this rather distinct horseshoe-shaped burrow there. Now the great thing is although we don't have the organism itself, this particular type of burrow, we know what age it's from. So we know that this particular type of burrow is produced in sediments which are of lower Jurassic age, and so we can use it to date the sediment, and we can also use it to correlate layers of sediment over great distances. So even though the organism that made it isn't present, the distinct shape of the burrow is enough to allow us to use it as, as if it was actually a normal fossil. So here we can see some sediments. So you can see the ripples. You can see that the crests of them are going from top to bottom. But you can see across these ripples, you can see you have these tracks here. And these are examples of burrows. So this is a bioturbated sediment. And now this one isn't particularly badly bioturbated. You can see the burrows, but you can still see the original physical sedimentary structures. However, if this burrowing was to be more extreme, obviously you would lose the original physical sedimentary structures, and that would unfortunately be a rather annoying loss. In terms of tracks, here you can see now we actually do have the fossil in this case. Here's a horseshoe crab, and you can see the tracks that it's left as it's coming along. So you can see there's one set of limbs there, and there's the other set of limbs there. Now the really interesting thing about this particular sample is when horseshoe crabs tend to move, they tend to move in pretty straight lines. What you'll notice about this particular track here is that it has quite a curve to it, doesn't it? It's not a nice straight line. And so what we're seeing here is we're seeing a horseshoe crab that's in distress. Something is clearly very, very wrong. The horseshoe crab is probably dying at this point. And instead of being able to walk in a straight line, it's literally stumbling around on the seafloor. And we can see its final moments in the form of its tracks. Slightly macabre, I know, but also extremely interesting in seeing what was happening in the past. And then here we have an example of a trace fossil, so essentially a biogenic structure which has been produced by us. So this is a human footprint, but we can see quite some interesting information here. So number one, the sediment that's being moved across has mud cracks in it. So we know we're in some kind of environment where we have a wet mud that's being exposed. The other thing is that the human being is moving across this mud before it's had a chance to fully solidify and become solid. So if you imagine moving across a surface like this, you can see how hard baked that clay is. So if you walked across this, it would be like walking across cement. In contrast, when this human being was walking across it, the sediment hadn't fully dried out yet. And so that allowed the human to actually leave the footprint behind. And so that's, although that doesn't give you too much information, from a sedimentary's point of view, it gives you some, useful information about what the environment was like, So obviously sediment was being exposed probably early in the day, and then, it was allowed to dry out, it started to crack, and then later on in the day, human beings were moving through the area, and one of them left a footprint behind as they went. So these are the structures we looked at. So these are the physical structures, and these are the organic structures. And we will combine the physical structures, the organic structures, and the physical properties of our layer of sediment together to produce our probable environment of deposition. That's what we're aiming for as a geologist. So, right, now we need to think about our interpretation. Now, we do have a slight problem. No sedimentary structure is exclusive to one regime. So you don't always get symmetrical ripples in a beach environment. As I said, you can get them in different environments like tidal estuaries, or you can get them in environments like along the margins of lakes. So if you see a symmetrical ripple, it doesn't instantly mean you're looking at a beach. So you have to use all the evidence available to you to come up with a defendable environmental interpretation. So you can't just rely on one thing. So another piece of information that we can use is the geometry of our layer of sediment. So what would it look like if we were able to view it in 3 dimensions? So the vast majority of sediments are simply deposited as a layer. So in terms of the sediment itself, you get the initial layer itself, and the geometry of the layer can also sometimes be modified. So it can be modified during compaction of the sediment, or maybe through erosion or deformation. So we always have to be aware that sometimes the geometry that we're looking at may not be original. It could possibly have been affected by a later process. However, if we are careful and we use the geometry in a conservative manner, it can be a very, very helpful piece of evidence. So as I was saying, most sediments will be deposited as a layer, and this layer will typically be maybe centimeters or meters thick, but it will extend laterally over distances of hundreds or maybe even thousands of meters. So you end up with a layer that's very, very broad, but very, very thin. And so these layers are described as having either a blanket or a sheet geometry. Okay, they mean the same thing. So this is the standard type of sedimentary layer. So most sedimentary layers will give you a blanket or sheet geometry. Now, if we're looking at a river-related sediment, on the other hand, if we're lucky, we might actually be able to find the river channel itself. So the river channel is a moderate energy environment, so it's going to have lots and lots of sandy material in the channel. The muddy material is going to be outside the channel on the floodplain. So the river itself will be visible in the sedimentary sequence as a line of sandy sediment. And this line of sediment is described as having an elongate or shoestring geometry. So if you were to look down on this layer of sandy sediment, you would see that it wiggles around the map a bit like a river. And so if we can, put together enough outcrops and be able to trace our elongate body of sandy sediment so we know where it goes, and we can see that it has this shoestring geometry, well, that's a very, very good piece of evidence to suggest that what we're looking at is a river channel. So in this instance, what we have is we have a piece of evidence that allows us to say with, okay, a reasonable amount of certainty that we may be looking at a river channel. However, we do have to be careful, because you can also get elongate or shoestring geometry formed by barrier islands. So a barrier island is essentially a sandbar that forms off the coast. So it runs parallel to the coast. So what you end up with, if you look in the rock record, would be a linear body of sand. Now, most of the time you can tell the difference, because an ancient river will wiggle around all over the place. It will meander. A barrier island, on the other hand, tends to be a more linear feature, tends to be more straight. So if you have enough outcrops that you can map, you can work out the geometry of it, and you can say, right, is this a river or is this a barrier island? However, if you don't have enough outcrops, so you can't actually map the feature itself, it can be quite difficult to distinguish between barrier islands and rivers based on that structure alone. However, we're smart people, and we know that barrier islands, as they form in a marine environment, will be quite likely to have pieces of shell mixed in with the sand. So what we would fall back on in that instance is we would look at the fossils. And in a barrier island setting, we would expect to find marine organisms, or should I say marine fossils. So maybe things like bits of oyster shell, for instance. In contrast, if we have a elongate or shoestring sand body which is associated with a river, which is going to be fresh water, we would expect to see freshwater fossils in there. So once again, this is another instance where we can't just rely on one piece of evidence. We have to bring in other pieces of evidence to back up our hypothesis. So there are a couple of other geometries that turn up. Deltas have a very distinct geometry. So if you look at a delta from the top down, it has what's referred to as a lobate geometry, so it looks like a semicircle, or more accurately like a fan. So it starts off narrow at one side and it broadens out. So this is if you look at it from the top down, and I have no idea what's happening to my spelling right there, I do apologise. But if you were to take a slice through your delta, what you would see is something that looks like a lens. It has what's called a lenticular shape. So if you take a cross section through a delta, it will look like a lens. Think of something that looks a bit like a football. So starts narrow at one end, broadens out in the middle, and then narrows at the other end. But if you look at a group of delta sediments from the top down, what you'll see is this lobate, this fan-shaped feature. The final type of feature that we might see are features associated with buried reefs. So a reef is a linear body, but it's often quite irregular as well. It's often not one solid mass because it's made up of concentrations of dead coral, essentially. So what you have is a rough linear body made up of lots and lots of coral fossils. And so in the case of in that instance, what you have is you have double evidence. So you have this irregular linear body, and then you can combine that with all the coral fossils. And so that's going to allow you to come up with your interpretation for the environment of deposition. So finally, we also need to think about the fossils. So, of course, fossils represent the remains or traces of prehistoric organisms which are preserved in the rock. And they're very helpful to us. They can help us work out that, we can date the rock using them, we can correlate layers of rock from different areas using them, and of course they give us a very good indicator of the type of environment the sediment was being deposited in. So the other thing about fossils is, of course, they are quite important constituents of certain sedimentary rocks, particularly limestones. So when present, fossils are extremely helpful. So we love fossils. Now, two factors must be considered when we're using fossils to help us work out the environment in which our rock formed. The first question is, did the organism in question live where it was buried, or was it transported? So let's try and think of an example. So if we were to find dinosaur bones, you would typically assume that means the sediment you're looking at was deposited in a continental environment. So maybe something like a floodplain, and that would be reasonably logical because dinosaurs lived on dry land. However, if the dinosaur bones occurred in a bed, a rock, along with coral fossils and other shelly organisms, so let's say bits of oyster shell, well, then something's a little bit off. And so we would have to assume that either the carcass had been washed out to sea, or maybe the dinosaur had been killed by some kind of tsunami, in which case all these bits of coral and bits of shell were washed onto the land. So we need to, look, we can't just rely on the fossil itself, we also need to try and use the rock that it's in to accurately gauge, what happened to that fossil. Did the fossil actually live in the environment which the sediment represents, or is the fossil an external organism that's been transported in after it died? So the other thing we need to think about is what kind of habitat did the organisms originally occupy? Now sometimes this can be quite easy. So for something like a horseshoe crab, we know horseshoe crabs tend to prefer shallow water. They tend to like water that's a little bit muddy, and they tend to prefer warm water as well. So, when we find a horseshoe crab fossil, that's relatively straightforward, and we can be relatively certain about that because, of course, we have modern horseshoe crabs. So that allows us to extrapolate the environments that ancient horseshoe crabs used to live in. In other cases, it can be a little bit more difficult because, of course, for extinct organisms, you can never be 100% certain about exactly what type of environment they like to live in. However, you can feel relatively confident for a lot of organisms. Another thing we can think about is we can look at the structure of the fossil. So, for instance, was the shell of our organism thick or thin? Well, obviously, a thick shell would suggest that your organism was trying to protect itself, so it lived in probably in an environment where there was quite a high rate of predation. You know, is your organism elongate or equant? Well, you know, depending on the type of environment your organism is living in some instances it may be an evolutionary advantage to be long and slender, so elongate like a pencil. In other environments, it may be more appropriate to be more equant, so more equal in all dimensions. Did our fossil have spines, for instance? So think of something like a sea urchin covered in spines. Why did it have the spines? Well, it obviously had the spines for defense. However, there are also some sea urchins that don't have spines, and that's because they actually live in the sediment of the seafloor. And so if you think about it, if you're a sea urchin and you're covered in spines, well, that's obviously going to make it very difficult for you to move through the sediment. And so this is another thing we can look for to try and gauge what was going on. So where possible, it's useful to study the fossils that are living now. So for instance, if you think about clams, well, clams tend to have quite a thick shell. That's because they typically live in shallow marine environments. So these are environments that are often very, very rich in life, and so there are lots of predators. And so that means the clam has to defend itself. And so one of the easiest ways to defend itself is to have a big, thick, impenetrable shell. In contrast, if you're a clam that lives in deep, cold water, so a very low energy environment, you know, think of something like the abyssal plain, for instance, well, in those environments, you're obviously going to have a much lower rate of predation. And so in that instance, is it really worth expending your energy on producing a big, thick shell? The answer is no. And so what we tend to see is we tend to see organisms that live in quite deeper, low energy environments, or in very, very cold environments like the Arctic Ocean or the Antarctic Ocean, tend to have thinner shells because there are lower rates of predation, and so it's not, you know, it's not a logical thing to waste a whole load of energy producing a big, thick shell that you're not going to need. So another example, the types of things we can look for are things like corals. Well, we know that corals like to live in shallow, warm, clear water. So the question obviously becomes, well, why? Well, the thing about shallow, clear, warm water is it's the perfect environment for little single-celled or very small multi-celled organisms to live. And so those environments are going to be full of things like algae, which of course the corals and other animals can use as a food source. And so simply by looking at the fossils that we have and thinking about the type of environment in which we're going to find them and why they have the adaptations that they have, that's going to let us get a better handle on what environment of deposition we might be looking at. So another thing we can look at is the microfossils. These are the fossils we can only see when we use a microscope. Now, they're very useful as multiple species and examples can be gathered from a small sample. You only need a small piece of rock, and from that small piece of rock you can gather multiple microfossils. So in something like oil well drilling or gas well drilling, you'll typically produce lots and lots of rock chips, so pieces of rock that are produced as part of the drilling process. And so these get brought to the surface, and the geologist can recover them, and you can actually, you know, take these rock chips and analyze them and look at the microfossils. Now, the nice thing is that, you know, each one of these rock chips can contain thousands of microfossils, so you don't need very much material to work with. And the microfossils are useful because they allow you to date the rock, they allow you to correlate layers of rock over large distances, but they also allow you to do an environmental analysis. And the thing is they're useful because some microfossils can tell us about things like water depth, water temperature, the amount of light there was in the water, the abundance of nutrients, to mention just a few. So some microfossils have very, very limited environments in which they like to live. And so we've managed to work out what environments they like to live in. So every time we see that particular organism in the fossil record, we know these were the conditions in this area at that time. And so microfossils can often be very, very helpful in working out what the conditions were like in that environment. Obviously, it's also very important in the oil and gas industry, because what you really want is you want to have a rock that was forming in the right conditions. So obviously, if you want a rock that's going to give you oil or gas, what you really want is typically a muddy rock that has quite a lot of organic material in it. So you really want a very highly productive ocean environment that's going to produce lots and lots and lots of organic material that can get mixed into your sediment. And so the microfossils can tell you, exactly how good or bad the environment was. So the final thing is we've already discussed how sometimes we don't have the fossil. The fossil itself can be lost, but we do have the trace. So the trace fossils that get left behind can also be indicative of certain environments. So as we've discussed horseshoe crabs, we know that horseshoe crabs like to live in shallow water, typically warm and normally muddy. So if we see horseshoe crab tracks, we have some idea of the type of environment we're looking at. But we can also use burrows. So we actually have these things which are referred to as Ichnofacies. And this is the process of using the burrows in the sediment to actually work out where you are in the marine environment. And what you'll notice is as you go from the coastline to the abyssal plain, you actually get different types of burrows associated with different environments. And so as a geologist, all you have to do is you just have to find the burrows. So here we have an example of a sediment containing burrows, and we then have to identify which organism has produced them. So if we have a look around, there we go, 28. Okay, so we know this is going to be the organism in question that produced these burrows. Once again, the organism itself isn't present. The probably rotted away. However, the burrows it produced are still there, and so what we can do is once we've identified the type of burrow, we can then go and find the correct Ichnofacies, so we know that this particular sediment represents an abyssal zone, so we're in the deep, deep ocean. And so, once again, even though we don't have the fossil itself, we can use the trace fossil to work out where we are using these Ichnofacies. Okay, so those are some of the things we like to look for when we're dealing with sedimentary rocks to try and help us work out what environment this sediment was deposited in. And so the next presentation is going to be looking through several different environments of deposition. We're going to go through them each one at a time, and we're going to work out what the indicators, the criteria are for each of those different environments of deposition. Okay everyone, thank you for listening and have a good day.